We're going to talk about an important application of orthogonal projections. This is something called the linear regression problem. This kind of thing appears a lot in statistics and throughout all experimental branches of science. And basically the problem is to find the equation of the line that best fits your data points. So a lot of ideas in science have linear models. So for example, V final equals V initial plus AT. That's a theoretical model. But what we do is we do experiments and we collect data points, xi, yi, and then we say, okay, what line fits those data points? So coming up with the slope and the y-intercept of that line will be solving our problem. We found the line that fits the data. So as an example of that, here's a very simple situation. Let's talk about the line that fits these data points, 2, 3, 3, 2, etc. So the idea here is that we need to come up with this linear equation with two unknowns, a slope and a y-intercept. And what we do is we require that this line fits the data. And by saying that, fitting the data, that means whenever we plug in the coordinates of each data point, it must make this linear equation true. So for example, if I take that first data point, I will have that 3 is the output when 2 is the input. So this equation should be true. Now at the same time, if I go through and I plug it all in, I will get this type of thing as my set of relationships. So what you're going to see here is the following. Now, this ends up being a linear system, and it's a linear system for these two parameters, m and b. And we can then, therefore, write this in our usual way, right? So we can take all of these equations and write them as a set of linear equations, which they already are, but we'll put them in matrix form. Now, I'm going to talk about the unknown, the vector of unknowns in this particular situation, as consisting of two things. We'll have a b and an m. I'm just going to switch the order then from what you may be used to, just because it's going to make these equations look a certain way. Every one of these equations has a b, and that's why that first column of the matrix is filled with ones. The second column refers to all the weights on front of the slopes. And then the right-hand side is just the output values that we've got here. So this is our system. We are going to call this matrix A. This will be our vector x of unknowns, and then this will be our right-hand side. So it's just the same old ax equals b that we've been used to. So what we can then do is solve this system by doing an augmented matrix and doing the usual row reduction steps that we do. Now, you can pause the video and you can get to this final result. What you're going to find is that we're in a bit of a jam here. And what I mean by that is if you row reduce this system, you'll get to here. And if you take a look at those last two equations, these are contradictions. You cannot solve this system. Well, that's a problem, right? This system has no solution. So if my system has no solution, how on earth am I supposed to solve this problem, right? How can we solve a problem with no solution? As many of you know, when you do an experiment and you try to fit a line through your data points, it never lies on the line. So in general, you should never expect that the line will go through all the data points. It won't. And things like experimental error always get in the way, right? You will never be able to have all of your data points lie perfectly on the line. So by design, this is always going to be an inconsistent system. We always expect an inconsistent system. So then what does it mean for us to solve this problem? We can't solve it. So then the new goal in this particular case is for us to find a line that's as close as possible to all the data points. And I'm going to put the close in kind of air quotes because we need to define what that means. So we're going to try to find a line that's as close as possible to all the data points. So that really becomes the problem that we are working on. And as always, math people are picky, and we have to say, well, what does that mean, right? Now, a little bit more precisely, for our system AX equals B, we want to choose X so that this thing, AX, this matrix vector product, is as close as possible to our vector B. So that's what it is in a more general way of thinking, right? When we talk about our data set, right, we are saying here's a line, y equals mx plus b, x-axis, y-axis. If we have this line, we are going to be talking about predicted outputs. So the predicted output from the theory says if you give me an input xi, I should give you mxi plus b. And then we'll find the observed or the data output. Right? When you actually do the experiment for that value of xi, you get some different value yi. So for example, if this is x1, this would be m1, mx1b, and then it could be the case that you didn't actually see that. You saw this situation. And the same thing happens here. There's always this difference here. And we're going to call this, you can call this a residual. That's what stats people like to call this kind of thing, right? So the goal for us is we are trying to minimize these residuals. And in our setup here, AX would just be this matrix vector product that holds all of these different combinations. And we're trying to get this thing here, this thing as close as possible to this column vector that has the actual outputs. Right? And we're trying to do that by picking the M and the B here. So that's just me trying to put this into perspective back in the context of the original problem. What we are trying to do is figure out the two weights, this B and the M, so that that line is as close as possible to all of the observed values, not the predicted ones, but the observed. And in the context of this line, we're trying to make that column vector the same as the output column vector. So when we say, I want to get as close as possible, we already know what this is. This is just a projection problem. We've already been doing this, right? If you want to think about this problem in our linear algebra way, let's say there's our subspace. We are going to let W be the column space of whatever matrix A we've got. We can think of our output or the observed vector as this thing B. And the point of the story is that this B is not in the column space of A. It's not possible for me to write my line and have it go through all of the data points. I just can't do it. So when I talk about trying to find the best solution or the line that gets as close as possible, we want this AX to be as close as possible to our vector B. Well, we already know what vector does that. we know that b hat is the closest vector in the vector space to b. That's the point. We already know that this projection, the orthogonal projection, is the best we can do. If we are limited to being in this plane, that means that b hat is the vector that will do the best job. So that means for us, the best approximation to b is this thing b hat. And we can think of it as saying b hat is just some linear combination of all of those columns of A that we've got here. And this is going to be something we call our least squares approximate solution. Now, why would we call this a least squares approximate solution? Because the idea here is that when I say b hat, and I say that it's the closest to b, it means that if I were to take the length of this thing b hat, or sorry, if I were to take the length of b minus this b hat, which is the same as b minus ax hat, it's going to be less than or equal to the length or the distance from b to any other linear combination in the plane. This ax is the linear combination that's as close as possible. Now, this, in terms of the language I was using in the picture before, is just given by expressions that kind of look like that. And if you think about it, what we are doing is we are calculating the difference in a bunch of squares, right? That's how we calculate the length. And because of all of those squares that are in this length, this is why we say it is a least squares approximate solution. So the idea here is that we are going to try to find, just using the columns of this matrix, the answer that is the best or the closest to b, right? We are trying to get this thing as close as possible to the vector that we've got that is not in the plane. And so to do that, we are going to be solving a different problem. We are going to be trying to find this. So instead of solving ax equals b, which has no solution, we are going to solve this. Ax hat equals b hat, which does, by definition, have a solution because we are trying to build this thing b hat, which is in the column space there. And this would be what we call our approximate solution. This is our best guess. So to go ahead and solve that, we will try to take a slightly different approach.